Hi everyone, I'm Samuel Sisson.
I'm Matt.
Brad.
I'm Brad.
And our project was the Smart Biomimicking Solar Shrub. Now, our design problem was simple enough. Solar energy is the cleanest and most abundant renewable energy source available. But if you look at it, according to a 2015 report from GTM Research, roughly 77% of Americans are unable to get rooftop solar. That's over 90 million American households. And if you really look into it, getting rooftop solar is realistic only if you own your own home, and you can afford the expensive upfront costs or have good credit, and you have good roofing, you don't have issues with any physical barriers such as a big tree covering your roof, and you live in a state with policies that require utilities to compensate you for the energy you produce. Now our solution, a cheap, portable fake shrub with solar panels for leaves. It'd be something that could easily be placed on a patio, in a backyard, or on a balcony. And so, in collaboration with a team of mechanical engineers, we designed and developed a solar shrub that we hope to introduce more people to solar energy at home. So our design goals were focused on practicality. To be practical, the shrub must be able to utilize low power embedded hardware, able to optimize panel configuration to maximize energy collection, able to rotate to change orientation and increase in light exposure, and be simpler to use and install than conventional solar. But most importantly, be significantly more affordable than conventional solar. So pass it over to Brian.
Okay. So for low power, we use the MSP 432. The MSP 432 will essentially operate in a low power mode, only to interrupt every so often with a periodic interrupt. In that case, it will check the cluster voltages and optimize the panel configuration and rotate accordingly. The real-time clock, which we use for the periodic interrupts, is an onboard MSP 432 implementation. So it interrupts after a certain amount of preset time, and the preset time can be set to 1 minute, 1 hour, or every so often according to the time set in the real-time clock. The real-time clock functions include an initialization for the ports, so we can use the least amount of power, and also an initialization for the real-time clock for the day, month, year, and also the time of day. And hand over to Brad.
So talking about solar panel configuration for a little bit, as we can see, this is a diagram of what we have. We have 14 different clusters, and each cluster is 5 of these individual solar panels connected together in series. This is to reach our voltage, optimal voltage for charging our battery that we needed, which was determined by our inverter in order to put power back to the grid. So these are all connected in a way that they can be dynamically configured because they are grouped together in pairs, and we can change the wires with relays that we have set up. So here's a picture of the relays that we use inside the plant, and again, the MSP 432 can change these, which is essentially changing the wiring dynamically. So we use an algorithm that will gather and categorize the data from the sensors that we have, which these sensors are just the voltage of the clusters that are read by an ADC. And it'll determine what is best for mapping between series and parallel to determine the most efficient use of our wiring to generate the most power. So the microcontroller adjusts the solar panels depending on cluster voltage. So we did some small scale testing. This testing was conducted in ideal conditions. We used, so we assessed the optimal cluster configuration for the relays. Each cluster, again, in this small scale testing had 5 solar panels. We found that the 3 clusters in series resulted in the lowest power gain, while when they were in parallel, they produced the most power. But the problem with this is when they're in parallel, they have a lower overall voltage, potential voltage, which means if it's shaded or partially cloudy, this could not produce the voltage required in order to provide power to the battery, which would then make its overall power being generated essentially zero. So our idea to compensate for this is, again, to dynamically change this so that if it's partially cloudy or shady, we're boosting the voltage by putting these in series. So instead of doing nothing, it's still producing some current, even though it would be less than ideal. This is for pair testing. So we were testing individual, we saw those 14 clusters grouped into 7 pairs. So we were going through the pairs, activating one pair at a time, and we can see the important part of this testing is some of the cluster or pairs, when we activate them, have a decent jump in power, while others do not have that high of a jump, and that's because some clusters are not above that threshold, meaning when we activate the series configuration, it's bringing the clusters that are not above that threshold together with another cluster that's not above that threshold, and we're actually then producing more power. And so, talking about our cluster voltage sensors, which is how we determine how much sunlight each of these clusters are getting. Here's a picture of it. It's it's a circuit that steps down the voltage. It's a 24-to-1 ratio, so that essentially we're taking the highest possible voltage and making it so that our ADC can then read it, which we're using the MSP432. The maximum voltage we can use for our ADC is 2.5 volts, and the maximum for the clusters when they're in series is 60 volts, so we need to step that down to where we can read it.
So, as mentioned already, we use the MSP432's 14-bit ADC to read the values from our solar panel clusters. Since we have 14 clusters, we're going to be using 14 channels that the ADC provides. So as mentioned, 14 channels, they're going to be used to read the voltages. The ADC alone utilizes 2 functions, one for initialization, and then one to actually read in the ADC values. Additionally, we use the microcontroller systic interrupts to check if a flag has been raised that lets us know that the ADC values are ready to be read. Additionally, we want to rotate the plant so that it collects the most amount of solar energy. So to do that, we utilize a stepper motor to rotate at this pace. So we periodically will rotate the entire plant a full 360 degrees, and we do it in 30-degree increments and check to see what the values of the ADC are at each 30-degree increment. And again, this would allow us to optimize the energy collected by the plant. And after rotation of the plant is done, we then will reverse the plant back to the best position that it has determined. And then these are some of the stepper motor drivers that we use. They were written in embedded C using the Texas Instrument Code Composer Studio IDE. Our motor functions include initialization, clockwise rotation, counterclockwise rotation, seek, accelerate, and decelerate, and of course max speed. So when we were testing the stepper motor, again, it was to determine the best, the best way to have the plant collect sunlight. So when we did testing, we measured current values to monitor if it was even worth it to rotate the solar shrub. So we recorded maximum and minimum current values when all clusters were in parallel. And this is through small scale testing what we found. So in our small scale testing, without rotation, we found that the minimum current collected was 20 milliamps. After some rotation at 30-degree increments, we found a maximum position to be 47 milliamp current. the rotation.
Stutter's not supposed to be there, I guess it's just
Yeah.
doing that now.
And that's not the plant vibrating, that's
Yeah.
just the video.
Yeah.
Okay, so I guess I'll take over.
Yeah.
And so like one of those final features we talked about, the most important thing is reducing the cost. Trying to make this a really, not perfectly cheap, but cheaper option. So when we look at reducing costs in manufacturing, there are basically two ways to do it. You can either reduce costs by reducing cost of materials, or you can reduce the complexity. So our first step was everything you see in front of you, all the structural material, is 3D printed. We have over 160 parts that we 3D printed. But that sounds really hard, right? So how do we reduce the complexity? Of these 164 parts, there's 16 designs. The vast majority of them being just individual, either going into the pot design, which is 3 parts, the gears, which are 2 parts, or the stock itself, which is 5 parts. The same template. There are 3 branch templates, and 1 leaf template, and 1 cover template. And that makes it much easier for us to mass produce this. For our electrical subsystem, a significant number of consumer off-the-shelf parts, or COTS components were used. Things like our grid tie inverter, the MSP432, P401R, our relays, our step-down power supply. And no extraneous sensors were added. We didn't want to add overcomplications for this manufacturing. We didn't use photoresistors, photo sensors, and we purposely avoided doing things like IoT integration because we didn't want to have to add any kind of interface to deal with routers or access points, and then a server side to deal with that. And finally, for reducing the cost of materials, what we couldn't buy, we custom made. And so we made our own power bank of 18650 lithium cells, which we spot welded together. Our stepper motor driver is made from an L293D. So instead of buying a $50 driver, we got a $4 chip. And our ADC hardware we all made on a proto board with just a couple packs of resistors. So when we look at our cost analysis, we spent $699.21. A lot of this goes into our most expensive components, being our solar cells, our actual spot welding machine we used, and then our grid tie inverters. Because we made our own lithium battery bank, that allowed us to save a huge chunk of money for our capacity of 22 volts, 6,600 milliamp hours. We could not at all buy that, but we could make it for a significantly reduced cost. Again, making our own ADC board meant it was only $9 for our ADC, for our step down. Our most expensive thing was we used a Noctua fan, which was we wanted a really quiet cooling system in this. Other than that, for the battery bank, it was buying the cells, the BMS, and then the adapters to actually put it all together. All of our relays, we used opticouplers, which meant it's optically isolated. This helped us avoid blowing our board, because we did do that once. If you look closely, you can see we bought 2 MSP432s, because our first one went up in smoke. Other than that, we had our stepper motor and our L293D. These we were both lucky to actually already have, so we didn't have to go out and purchase them. All of our wiring used in this was about $50, but we have over 350 feet of wire running through this plant right here. And then we use a system with protection diodes to prevent backflow from the battery through our units. So of our budget, we had a budget of $700. We spent $699.21. So we came in under budget. But if you include the things we already had, we technically only spent $638.30. But that kind of brings us to, speaking of, killing the microcontroller. Actually, never mind. Later segment. Prototype design. This came into sort of working with the MEs. We worked with a team of mechanical engineers. There was a lot of time that went into this. I'm going to jump ahead just for a moment. We're going to talk about problems. So the segue works. Design comes into it. So our first thing we'll talk about is the 3D printing and assembly. We went through 3 full builds of this, trying to get our structure laid out. I'm sure all of you in the back have seen us carrying around these big plants trying to get them to work. We've used many spools of filament, and there's been a lot of learning going involved with that. Whether it be trying to figure out enough area for things to fit. Our original designs, we're all using friction fit, which is basically trying to make it so both the leaf and the branch, the whole side is anchored enough that you can just slot it in and it'll stay. That did not work. So instead we had to switch over to using some hand sanding and super glue, and then we had to switch over with also, like for our covers, we were going to use a tab system. And again, we had accuracy problems, so we had to switch over to super glue. Now problems like this could be avoided in a manufacturing sense just by having a better system. Because we 3D printed everything, it meant we were limited by the quality of our printers. If we were doing injection molding, something like that, it could be much faster and have a much lower error rate. And so when we look at our designs, our original prototype was going to have these curved panels, and we're going to have each branch basically support all of these just with this friction fit over here. And the biggest problem was trying to actually get this curve to work. When we take the panels, we use these organic thin film organic cells, and so they have some level of flexibility, but they won't hold that arch in the center. And so what we ended up having to do was switch over to this flat panel design instead. And then when I talked earlier about the battery, this is actually what our battery looked like. It was just a set of 15 18650 cells. We did 5 in series to create our 22 nominal voltage, and then 3 across to increase our capacity to 6,600 milliamp hours. And then, as you can see in front of you, this is our final design. Pass it over to Brett.
Talking about the solar cell manufacturing, this was a task given to the mechanical engineers. Their plan was to fabricate their own solar cells. They were going to devote an amount of resources into that, but that did not work out because of the various processes involved. So we ended up going with already assembled solar cell that was organic and flexible with thin film, but it does not have necessarily the efficiency that traditional like silicon solar cells have. So it's more of just a concept instead of something that will provide a large amount of power.
And originally we were going to go with something more of like a real kind of low power mode, which involved going into sort of the manual and looking into like the different modes. So they have like low power mode 1, 2, 3 I think, and 3.5. But ultimately we decided to use this sort of like a wait for interrupt and sort of make it sleep rather than go into the low power mode, which would involve using a different clock as well as, well, you couldn't get it to work ordinarily in the debug mode as well. So that turned out to be a problem when we were testing it. So we ultimately decided to just go with the sleep and wait for it interrupt.
And so in conclusion, the overall goal of this project was to create a means for individuals to utilize the benefits of solar energy. We've met this goal by having our solar shrub be low cost-ish, aesthetically appealing-ish, and having a lower power consumption. Our references are here, and our last thing is we really just wanted to do a huge shout out to our team. We had a huge amount of mechanical engineers and they worked around the clock trying to get this design figured out. We went through over 10 kilos of filament, and it was a huge, huge process. A special shout out to Hadi. And that's it. Any questions?